Alright, so before I get into my paper, I'm going to give you all a simple analogy. You guys can probably already solve this. So, cow is to milk as chicken is to what?
Egg.
Yeah. So, that's basically what an analogy is. You're given some set of information, and you're supposed to use that, find the pattern, and solve for the blank. Let's move on to another type. You're given a 3x3 matrix with the bottom right square empty. You're also given 8 answer choices found below. You're supposed to choose one of the 8 answer choices and see which one best fits the blank. I'll give you all a minute to solve this. You can discuss and raise your hand when you have the answer. Bless you.
The top right one?
This one?
Yeah.
This one?
Yes, that.
And why did you get that?
I just looked at the arrow, the triangle, and the square to the side, and then it's the circle, the box, and the. I don't know what that is.
Yeah. That's right. So you found the pattern between the leftmost object and the rightmost object. So why are analogies important? Why did I do this? Analogies are the cornerstone of human intelligence, meaning people use them in their everyday lives to develop useful inferences and develop novel abstractions. So if you think about it, school as a whole is just a large analogy. Every teacher, every course is asking you to apply what you learned and use what you learned and apply that to present-day problems. For example, if you think about math class, your teacher gives you a set of theorems and formulas, and you use that to the current problem at hand. Any questions? So my paper is titled Modeling Visual Problem Solving as Analogical Reasoning, otherwise known as Creating a Model to Solve Analogies. So the analogy that my paper is based on is called Raven's Progressive Matrix, or RPM. This is what you just took. You're given a 3x3 matrix and 8 answer choices, and you're supposed to solve for the missing square. But why did the modelers choose to use RPM tests as the basis for their model? Quite frankly, I'm willing to say that most of you haven't even heard of RPM tests. Well, they're used across the world to test for fluid intelligence, which is the ability to reason, think abstractly, and develop answers. They're good because they don't rely on any domain-specific knowledge or verbal abilities, meaning there's no discrimination against any culture, race, or language. Interestingly, participants who do well on RPM tests also do well on other standardized tests. So how was this model built? I'm not going to go too in-depth on how this model is built, but essentially it was built off of 2 pre-existing systems, CogSketch and Structure Mapping Engine, or SME for short. CogSketch is used to take in input information and generate a list of features. For example, in the previous problem, in the first box, it notices that there's an arrow on the left facing towards the left and a circle to its right. Structure Mapping Engine is the powerhouse of the model, meaning it performs all the comparisons between objects, images, and patterns of variance. So back to this question. How did you solve this again? Anyone?
Want me to repeat it?
Sure.
It pretty much just mirrors the left side.
Okay, so an object changes some way, right?
Yeah.
Yeah, so interestingly, that's the second most common way humans use to explain how objects can vary. The first being object stays the same, pretty simple. Third, 3 different objects in each order. Say there's a square, triangle, and circle in the first box, triangle, circle, square, then triangle, square, circle in the third box. Fourth, add or subtract objects, pretty simple. And the fifth one being each object is only in 2 of 3 images. That last rule seems pretty simple, but when you actually try to solve it using that rule, it's quite difficult because it takes up a lot of memory. So knowing that, how would you approach this type of problem? I'll give you all a minute and you can discuss and raise your hand if you have the answer. Yep. Which one? This one?
Yeah.
Sorry, that's incorrect. Amanda?
The on the bottom, the third one to the left, or the second one from the right.
This one?
Yes.
Sorry.
No. The one. No, I'm sorry. On the Sorry.
Yes, that's correct.
I said bottom. I meant top.
And how did you get that?
You notice that there's consistently a white box on the top right, and then you can tell that it's gonna overlap in the left bottom corner, because on the bottom one it's all the way gray lines vertically, and then coming down from the bottom there's always gonna be black lines that are horizontal, and then they overlap.
Yeah, you're correct. So how would a model approach this type of problem? This slide is going to be a mouthful, and I'm going to go more in depth into it in the next one, but this is just a general overview of how it's going to solve it. So step 1, it uses the CogSketch program in order to generate a list of features for every image. So for example, in the first image of the first problem I showed you, it notices that there's an arrow facing towards the left and a circle on the right. The second step in this process is it takes all the images in the first row and compares them with each other in order to find what's called a pattern of variance, which is just a list of differences between each image. Everyone with me? Okay, so the third step is the exact same, but instead of the top row, it performs it on the middle row in order to find its own pattern of variance. With those two patterns of variances, it compares them in the fourth step in order to generalize and create one common pattern of variance in order to, finally, in the fifth step, infer the image and project those differences onto the blank square. Hopefully, if its calculations were correct, it'll solve the problem. So let's apply that to this problem. Step 1, it'll encode every row. So if you take this square, for example, it notices that there's a circle on the left and an arrow to the right of it facing towards the right, and so on and so forth for all of the 8 squares. Step 2, it'll compare every object in the top row with each other. So from the first to the second box, it notices that the arrow shifts 90 degrees and moves to the right. And it notices the exact same thing from the second box to the third box. The third step is to compare every object in the middle row. So it notices the same thing. In this case, it's a triangle that shifts 90 degrees and moves to the right. Because of those two patterns of variances, and they're very similar, they're almost the exact same, it notices that in every row, the leftmost object in the first box will shift 90 degrees and move to the right as it goes further along the boxes. Using that information, it can infer the answer for here, because this object, the leftmost object, the rectangle, would turn 90 degrees twice and move to the right twice. In the end, coming up with that answer. So let's move on to a more difficult problem. Give you all a minute again, and you can raise your hand.
The top row, second from the left. The 4, that one.
No, sorry.
It's a good guess.
Josie? Yeah.
It's definitely bottom all the way to the right.
The 4 triangles? Yeah. That's the answer. How'd you come up with that?
Each of the rows, there's one thing with 2, one thing with 3, and one thing with 4. So then, if you look at like the bottom row, there's something with 3 objects and with 2 objects. So then, that's 4.
Yeah, so you found the pattern 2, 3, 4,
Yeah.
and also there's a square, an L-shaped object, and a triangle in every row. So for this more challenging type of problem, the model resorts to a 6th step if it can't solve it by inferring the image. The sixth step is simply brute force. It'll iterate over each of the 8 answer choices, plug them in, and see which is the best fit. Whichever one is the best fit is its answer. So the first 5 steps are the exact same. It'll encode all rows, compare objects in the top row, compare objects in the middle row, and then compare those 2 patterns of variances with each other. However, because those 2 patterns of variances were different, it couldn't infer the answer based on those 2 pieces of information. So what does it do is it resorts to brute force, plugs each answer in, and hopefully it'll come up with that answer. Everyone with me? Okay. So how did it work? How did the humans fare against the model? Well, there were 42 participants tested, but 2 scores were removed because their scores were outliers. The mean performance was a 54 out of 60. So if you look at the score breakdown, as the humans move further along in the sections, their scores decrease dramatically, indicating that the questions become harder as you go further along.
Hey Jeffrey.
Yeah.
Do you know if there were time limits?
No, they were given however much time. But it was interesting because they found out that participants who generally spent more time on a question got those questions incorrect or wrong.
Thanks.
So the model solved 56 out of 60 problems, so only 2 more than the humans. But if you look at the score breakdown, the 4 problems that it failed on were found in both sections D and E, indicating that the problems that the model failed on were among the hardest problems for humans to solve as well. It shows that the model was modeled so well that it accurately modeled how a human would think under these test-like conditions. So back to this problem. What problems did you face when trying to solve this? Anyone? Drew?
It's like the idea that we wanted to mimic the pattern in the middle row, but it looked like there was already a square in the bottom left.
Yeah. So, I don't know if this is what you're trying to say, but I think that the overlapping lines caused you to, yeah. Sorry. The overlapping lines took up a lot of memory in your brain, so it was very frustrating to just keep track of all those lines. So this is one of the hardest problems for human test takers. In fact, it was the 6th hardest problem on this test. It's difficult because of the overlapping lines, as I said. It causes a lot of, memory overload in your brain. It causes you to become frustrated and just restart. But the model, however, was able to solve it with little difficulty because it was programmed with enough memory in the first place. So back to this problem. What problems did you face when trying to solve this one? Let's hear.
Well, for me, I got that it was 4 different objects, but I didn't see that the sides, the sides mattered. So I thought there were multiple options.
Yeah, I had, I think if you combined me and Alessi, you would have gotten it because I had the opposite problem. I had not figured out there were 4, but I figured out it must be the triangle because there weren't repeating patterns. And I was trying to decide between the 3 and the 4.
Yeah, so in this problem, there's a lot of things to look for. You're supposed to look for 2, 3, 4, and a square, triangle, and L-shaped objects. Also, I don't know if you guys noticed this, but the objects were much more abstract looking in this picture. So, if you look at the L-shaped objects, this is also an L-shaped object, but it's really difficult for humans and the model to recognize that. So, as a result, the model did not solve this problem. As you guys noticed, to solve this problem, you're supposed to look for a group of 2, 3, and 4 in each row. And you're also supposed to know that there's a square, triangle, and an L-shaped object in every row. If you look at the bottom row then, you notice that there's a group of 2, 3, but you're missing a group of 4. Also, there are squares, L-shaped objects, but no triangles. If you combine those 2 pieces of information, you're missing a group of 4 triangles. But this is really hard for humans and the model to solve because we're just not built to recognize abstract features. Questions? Yeah, Josie?
Did it analyze vertical columns at all? Or only rows?
Not in this case, but when solving RPM problems, you can do that. So that might be a thing we can code in the future. Yeah.
for the step of recognizing the shape. So if you take, for example, the mirrored triangles, right?
Yeah.
Computer programs usually have a hard time telling that those are the same thing. So if you took, for example, like different degrees of shifting directionality with all of those, how does it recognize that, you know, a triangle here versus a triangle here versus a triangle here are all the same shape?
It'll basically crop out that original triangle, and then it'll put the triangle there and just keep on shifting it to see if it eventually matches.
So it's kind of like iterative
Yeah.
trial and errors to try to see if it fits?
Yeah.
Got it.
So what does this mean going forward? With this model, we understand how a human thinks, so we can use that to create specific problems to target one's skills and weaknesses. For example, if that previous problem showed that most humans had difficulty recognizing abstract features, that's a sign that we need to work on teach students how to recognize abstract ideas. In the future, maybe we can just feed in RPM problems into this model. It'll spit out incorrect problems, which tells us that we need to work on those types of problems. Using that, hopefully we can improve students' standardized test scores, because RPM problems or RPM tests have a high correlation with standardized test scores. The better you do on RPM tests, the better you do on, say, the SATs, because RPM tests tap into one's core cognitive abilities. Any questions?